Welcome to this session on GPU-centric AI compute fundamentals. Today, we'll explore why raw compute power isn't enough for modern AI. We will uncover how GPU to GPU communication has become the defining factor in AI performance, and how technologies like NVLink and GPU Direct facilitate this. Let's begin by understanding the core problem. Modern AI is fundamentally a distributed computing problem. We are no longer training models on a single card, we are splitting massive large language models across thousands of GPUs. In this environment, the workload is tightly coupled, meaning all GPUs must synchronize their calculations constantly. If GPU A is waiting for data from GPU B, the entire training process halts. This wait time is what we call tail latency. Because GPU computation speeds have skyrocketed, the network that pipe moving data between them has become the new bottleneck. Therefore, the speed at which GPUs communicate now defines the total performance of the AI factory. This flowchart visualizes the dependency chain in AI training. When a model exceeds single GPU memory, move to distributed computing. As we split the model, synchronization becomes the critical juncture. If communication is slow, we get high tail latency, leading to stalls and wasted investment. If communication is fast, we maintain high GPU utilization, which is our ultimate performance goal. Solve the bandwidth issue inside a single server, we cannot rely on standard PCIe. Even Gen 5 PCIe at roughly 64 gigabytes per second is a bottleneck for modern AI. To address this, we use NVIDIA NVLink. This technology creates a direct high-speed highway between GPUs, delivering up to 8 terabytes per second of bidirectional bandwidth, significantly faster than PCIe. To scale this, use the NV switch. Think of NV switch as a traffic cop that allows every GPU in a server to talk to every other GPU simultaneously at full speed, creating a unified memory space that simplifies how we program these massive models. Compare the two architectures here. On the top, the standard architecture forces GPUs to communicate through the CPU via slow PCIe links. On the bottom, the NVLink architecture connects all GPUs, 1 through 4, directly to the NV switch. This creates a high-bandwidth mesh where data flows freely between GPUs without ever bothering the CPU. Scaling beyond a single server brings us to the network. In traditional networking, sending data from a GPU involved copying it to the system's CPU and RAM first, then to the network card. This bounce adds massive latency. We solve this with GPU Direct RDMA, Remote Direct Memory Access. Technology allows the GPU to access the network interface card, like a ConnectX or Bluefield Super NIC, directly via PCIe. By bypassing the CPU and system memory entirely, we achieve a zero-copy transfer. This drastically reduces latency and frees up the CPU to handle other management tasks, ensuring the network doesn't slow down the math. This sequence diagram illustrates the efficiency of GPU Direct. The traditional path at the top, you see two distinct steps, copying to CPU RAM then to the NIC. This is slow. In the GPU Direct RDMA path below, there is a single direct line from GPU memory to the NIC. This zero-copy method eliminates the middleman, reducing latency essential for distributed AI. Finally, hardware needs intelligent software to drive it. This is the role of NCCL, the NVIDIA Collective Communication Library. NCCL implements collective operations standard communication patterns like allReduce, where every GPU shares its results with every other GPU to update the AI model. NCCL is topology-aware. It automatically scans the hardware to determine the fastest path for data. The GPUs are in the same box, it uses NVLink. If they are across the room, it uses InfiniBand or Ethernet via GPU Direct. This abstraction allows developers to focus on the model, knowing the communication is optimized for maximum bandwidth. This diagram shows how NCCL operates. It starts with topology detection. Based on the hardware found, it moves to path selection. If it detects GPUs on the same node, it selects the intra-node path using NV switch. If the GPUs are remote, it selects the inter-node path using GPU Direct RDMA. Both paths converge to complete the collective operation efficiently.